Okay, good morning, everyone. Warmed up? You de-thawed? You feel all your fingers? Just wanted to start by going over a couple of things that seem to have become unclear with some, and that is, this is school policy. It's not mine. It's from the provost, but someone can attend class virtually and be counted present only if they have been told to isolate by a your college authority. And that is pretty much Megan Schruck. All right. But somebody in that office, if you've been told to isolate or quarantine, you can attend virtually and be counted present. Okay. The other exception, I guess, is times like Monday, where regular classes have been canceled by the provost. Okay. For inclement weather in that case, right? Anyone else is welcome to attend class virtually anytime you don't feel like getting out of bed or whatever, but you'll be counted absent. And that is what I'm told to do, and that's what I'm going to do. All right. The other thing is, and I don't know to whom this applies, but when you are attending virtually, your smiling face must be on camera. All right. So you have to have camera on, and it's got to be seeing your face. Live, your face. I've heard about people putting up pictures of themselves like this in front of the camera, right? And no, you got to see the person moving. Mute your microphone, paying active attention. So I just want to review that. Going over to today's, where we left off last time. I'll just underscore. And if you're not spending that hour or two between class periods looking at this, you're in for a disappointing result in chapter 3, right? And that is especially true if you did not do well on the chapter 1 and 2 tests, because you're weak in the prerequisite skills. I'm here to help you. Come by. My office is right below Jevon, as I've said before. I'm at every Spark. Spark unfortunately got canceled this week, but I'm usually there, and some of you are always there, so that's good. But I'm here to help. Last time we began a 6-step process of graphing a rational function. Some of these steps we've had. Some of these steps we have not had. Right? Some of these steps we have had. Some of them we have not had. Oh, we got some. Sorry, here I got some homework to pass back before I get started. Always got to check up here. There you go. All right. If we have a rational function, what is a rational function? It is one polynomial function divided by another one. We did some simple ones before this, but now we're doing one that's more involved. And so if you look back at our definition back here, we call the top polynomial p of x the bottom polynomial q of x. The top polynomial has, guess what? It is time to reorient the board. Sorry about this, folks. The board has gotten, with all these electricity going on and off, every time the computer does a hard reset, I lose the orientation of the board. So where I'm writing is not where the ink is going. All right, should be better. Let's try that again. The degree of the numerator is n. The degree of the denominator is m. So those are two of the first things you will identify when you see when you're asked to graph a rational function. So last time, we see the top is x plus 4. That's p of x, and it has degree 1. Degree is the highest power of x that appears. Q of x, x squared minus 4, has degree 2. Right? The first thing we did is we found intercepts. X-intercept, y-intercept. So we wound up with x-intercept or y-intercept of minus 1, x-intercept of minus 4. We put those on our graph over here on the right. Then we go to the next page, and I have those points already on your graph, although they won't be colored in on your paper, your pencils and stuff. You know, it won't be in your ink, but they're there. We're going to find vertical asymptotes. Vertical asymptotes. Now, there is a method to these steps. For example, you start off with two intercepts, y-intercept, x-intercept. For the x-intercept, when it's a rational function, that means a fraction equals 0 when the numerator equals 0. The top equals 0. And the top is basically solving p of x equal to 0, the top. For vertical asymptotes, you're solving the bottom equal to 0. Because the places, the values of x, for which the denominator equals 0, those values of x are not in the domain of the rational function. Let me say that again. Values of x that make the denominator equal to 0 are not in the domain. And what's going to happen if the denominator equals 0 and the numerator is not 0? You're going to have a vertical asymptote. Vertical is up and down, right? Like this. Okay? So to find those values that make the denominator equal 0 in our rational expression undefined, we solve q of x, which is, in this case, x squared minus 4 equal to 0. Let me tell you a common mistake on a problem like this. Somebody will do this. X squared equal 4, x equal 2. Right? And so 2 is a vertical asymptote, they say. Okay, so they'll go over here, and you'll draw a vertical asymptote at 2. Let's just do that. Right here. All asymptotes in here, todos, all asymptotes in here are denoted by a dashed line on your paper, even if they coincide with an axis, a coordinate axis. You dash over that axis. So that's that green dashed line. What's wrong with what we did here? Who can spot what is wrong with my work here? The square root of 4 is 2, but it's also minus 2. When you take the square root of both sides, you need to do a plus and minus. All right? Now, the other way to have done that is x squared minus 4. So these are those are your vertical asymptotes. I'm going to mark them over on the right in a minute. Another way of doing this is x squared minus 4 equals 0. That's the same as x plus 2 times x minus 2 equal 0. You factor x squared minus 4. That's a difference of squares. Factors into x plus 2, x minus 2. That gives you set each of those factors equal to 0, x equal minus 2, or x equal to 2. So you still get plus or minus 2 for your vertical asymptotes. And so you go over here, and you have another vertical asymptote at minus 2. All right? Now, any questions? Stop me. Please stop me if you need it, right? Now, let me just throw out an observation here. We don't know what the graph of this looks like yet, but the only places where this rational function can change signs is where? It can change signs by, don't write this on your paper, but it can change signs by like crossing at that x-intercept. We don't know if it crosses at the x-intercept, but a rational function could cross at an x-intercept. So an x-intercept is one place that a rational function can change signs. The other place is at a vertical asymptote, because at these green vertical asymptotes, the graph is going to go to infinity, plus or minus on either side. So the graph, when it jumps the asymptote, could go from positive to negative or negative to positive. So like over here on the right, it could go, we don't know how it goes yet, but it could come down from positive infinity on that side and come up from negative infinity on that side. It would have changed signs. Now, we don't know if that happens, and we're going to find out how you determine what happens at these points. But what I want you to walk away with from the last 2 minutes here is the only places at which a rational function can change signs. The only places at which a rational function can change signs is, drum roll please, at x-intercepts or at vertical asymptotes. Everywhere else, it stays the same sign. Everywhere else, it stays the same sign. So I'm going to erase those marks over there on the right. So, for example, from -4 up to -2 in this little interval right here, that little stretch right there, I don't know which sign the function is, but it doesn't change signs during that interval. It stays the same sign. Similarly, between these two asymptotes, the function stays the same sign. Now, we happen to know what that sign is here because the y-intercept is negative. So you know the function is negative for this entire interval from -2 to 2. Because there are no other vertical asymptotes or x-intercepts. And the same past 2, you know past 2, there's no more x-intercepts out there. There's no more vertical asymptotes out there. So it will not change signs. Whatever sign it is, it's going to stay that sign. The punchline is, you got to see the signs. You look for the signs. Got to see the signs here. Okay. All right. I said that so you'll more easily understand this slide. This is new. We have not had this yet this semester. Okay? We have not had this yet. This is horizontal asymptotes. Now, do you see the pattern? The first 2 are intercepts. The bottom, the second one, I mean, you set the numerator equal to 0. Step 3, vertical asymptotes, you set the denominator equal to 0. Right? Step 3 is vertical asymptotes. Step 4 is horizontal asymptotes. Every one of these steps kind of has a partner. All right? Now, horizontal asymptotes. This is another page that you probably need to mark. We're going to mark it with a heart for Valentine's Day, because you're just going to love these problems, right? So we have the star page we're going to go back to at one point, the asterisk page, and we're going to have the heart page. Remember this one because we're going to refer back to it a couple more times in the coming slides. Okay? Now, here's the key. This is the key. How do you start testing for horizontal asymptotes? How do you determine where the horizontal asymptotes are? Right? How do you determine? You compare N and M. That might be why that's in red. You compare N and M. What is N? Degree of the numerator. What is M? The degree of the denominator. You compare them. Now, if you compare two numbers, there are only three relationships two numbers can have, at least real numbers, right? Look in this column here, criterion, this column right here. Look in that column. There's only three relationships N and M can have. M can be bigger than N can be bigger than M, or they can be equal. The first one can be bigger than the second one can be bigger than the first one, or they can be the same. And depending on that relationship, you will draw your horizontal asymptotes, if any. There may not be any horizontal asymptotes. But if there are, you'll determine it by comparing N and M. All right? Now, we're going to do this one at a time. I'm not going to go through this whole table. The reason why is that by the time we need the rest of it, you'll have forgotten it anyway. But we're going to go here and say, okay, my rational function's over here. You remember that the degree of the numerator was 1. The degree of the denominator is 2. So notice, the student will observe, right? N, 1 is N. That is less than 2, which is M. So N is less than M. That puts you in this case here. So for this problem, we're in this case. We're going to do 2 more examples for these other 2 cases. Oh, by the way, I told you I was going to tell a story. I told you before I was going to tell the story about college algebra. 15 years ago, I had 2 young ladies in this class. This is the secret, by the way, to doing well. Well, a secret to doing well here, right? We used to teach on the chalkboard over there on the right. All this wasn't here. In fact, there wasn't even a wall here. There wasn't even a wall here. The top floor of SAC here was abandoned. I'm not kidding. It was an old elementary school. And back here, where Miguel is sitting, and then right behind her, there were 2 young ladies who sat here. Actually, where she's sitting and more like here, right here. The back of class had like 30 people in it, right? These 2 young ladies, they studied hard. They were on the same sports team. These 2 young ladies studied hard. One of them was just very highly intelligent. And I think she'd had a better background. She was solid A student. The other one was a solid B student. Give me a whole class full of students that work as hard as these 2 did. They were on the same sports team. The one young lady just mopped the floor in here, got an A, and that's when we used to cover more material than we cover now. She got an A, the other one got a B. Next semester, they're in my statistics class. Same 2 young ladies. I used to have my office right up there behind that wall, that little thing above the stairwell, right? I used to be in my office 15 years. They come in my office one day for help, and you know, we help, you know, we clarified their questions. And then we start talking, and I said, hey, you know, Susie Q, this one girl, that was not her real name. I said, tell me how you did so well in college algebra. And she says, oh, Mr. Miller, I didn't. And she was usually pretty frank about it, you know. I don't want to hurt your feelings. I go, try me. I promise I won't be offended. She says, well, whenever you act stupid and get all excited, I know that's going to be on the test. I go, perfect, right? Perfect. When I go plug in 0, you know it's going to be there, right? You know that's going to be there. Later that semester, they both got expelled from York College. I'm just saying, okay. They were always very polite, very well behaved, very nice young ladies around me. I'm still in touch with them, right? We became Facebook friends after that. They went to another college. They had, let's just say, a variety of behaviors on campus. And so they left York College. But my point is this. When I get all stupid about something, which is a lot of the time, right? You know that's going to be there. You put that down. Will be on test. Miller is stupid again. Okay? Now, here's another clue of something that's going to be on the test. We are going to spend the next week doing these problems. The next week. 3 days. Well, actually, a little bit of last time today. Friday, maybe some on Monday. I don't know. But when we spend a week on something, what do you think the probability you're going to have one of those on the test is? Guaranteed, or your money back. All right? You will have one of these, at least one on the exam. At least one. Maybe two. Maybe one on the calculator section and maybe one on the non-calculator section. Right? That's a hint. That's a hint. Okay. Right. So do yourself a favor. Know how to do these inside and out. Come to class on test day mad at me. I hate that class. Then shoot those points, put them in the bag, and walk out the door with a good grade, all right? You're going to have these because these bring together a lot of different skills. They bring together a lot of different skills. So back to this. You need to familiarize yourself with this entire table and these 6 steps because we're going to do this over and over again. Over and over again. All right? So now we know that n is less than m. What does that mean? That means the bottom has a higher power of x than the top. If m in the bottom is greater than n in the top, that means there's an x squared down here in this case and an x up top. As x gets bigger, which one's going to grow faster? The x in the top or the x squared in the bottom? The x squared is going to grow faster. So this bottom is going to grow. When x gets big, either very negative or very positive, when x gets big, the bottom is going to grow a lot faster than the top. So what do you have? You have a fraction, the top small, the bottom big. Right? Small divided by big is small. 1 divided by 1,000,000 is small. So that means the ratio is going to be small. And it's going to get smaller the bigger x gets. And so that ratio is going to go to 0. And so the graph will approach 0, which means that the x-axis is the horizontal asymptote. I tried to explain to you why. All right, and I can clarify that if you didn't get it. But if you didn't understand that, remember that when n is less than m, the x-axis is the horizontal asymptote for large values of x. Large values of x, not for small values, for large values. Okay? So now let's go back to our chart here. Right? Since n is less than m, the horizontal asymptote is the x-axis. So what does that mean? On your graph, you dash in the horizontal axis. Okay? Any questions on that? Since the numerator is of lower degree than the denominator is bigger, the ratio is going to go to 0 as x gets big. That means the x-axis will be the horizontal asymptote for large values of x. That means way negative over here or way positive over here. Right? Right? In the middle, it's going to do the loopy-droopy stuff. This is where it goes, woohoo, woohoo, all the fancy stuff, right? So the horizontal axis is the value to which the graph levels out. The graph's going to level out at that value for large values of x, positive or negative. So there, you have this here. All right. Now, you know what? We are missing something I see on here. We're missing two things on here, actually. We're missing this point here. Move that down. That point. These 2 points here. There. I'll put these on this graph here. Be sure to add them on yours. All right, that's 4 minus 1, right? Okay. So that's the evidence we collected so far. It's like CSI. It's like you're cracking a criminal case. And the graph is your evidence locker. You're collecting evidence along the way. Now what do you do? Now what do you do? You're going to plot points strategically. Strategically. Now's a good time for me to tell you another little hint. People who don't study this, what do? They go to the original graph and they start plotting points. They say x equals whatever, that means y equals this. They put x and y value, x values in and get y values out. And so what they do here is they'll get points like that one, they'll get that one, this one, and that one. Right? And then what do? They will take these and they'll connect the dots. That's the graph of someone who hasn't done one of these. That's the guess, right? And out of 10 points, it's worth exactly 0 because you haven't learned a thing if that's your graph. All right? So plotting points in general is a graphing technique. It's one of the first ones that you learn in algebra, right? You learn to plot points, x and y. It doesn't work with a hoot here. It doesn't work with a hoot. Because you can see, let me erase all that. You can see that it doesn't respect all the stuff we found. It doesn't respect our asymptotes and stuff when you do that. Because when you connect the dots, you're going right over these vertical asymptotes. And those vertical asymptotes are where the denominator is 0. So it has no graph at those vertical asymptotes. So that's point number 1. You're going to plot points here, not just any old willy-nilly way. You're going to plot points strategically. The second thing I want to say. You ready? These vertical asymptotes are electrified fences. What do I mean by that? Graphs never touch them. And when they do touch them, there's a problem, right? But what happens? They're electrified fences, and the graph is like, let's just say most little boys, when they go on a ranch, there's an electrified fence. The dad says, don't touch that. Don't touch that, son. What's the little boy doing? Why, Dad? Why not? Because it'll knock you on your can. That's why it's electrified. It'll shock you. Oh, is that right? So what does the little boy do every single time? They go, I'm not touching it, Dad. Look, I'm not touching. Boom, they're on their can, right? So the graph is going to get very, very close to these two, but it's not going to touch. Just like the little boy's trying to do. It's not going to touch. That is vertical asymptotes. Vertical asymptotes are never touched. They're jumped. The graph will jump one side to the other. It will never be that value. Horizontal asymptotes, on the other hand, are not electrified fences. They behave like electrified fences for x's that are very small over here, way out here, and x's that are very large out here. In the middle, for relatively small values of x, horizontal asymptotes can be crossed and touched. Graphs do cross and touch them. And an example of that is right here. There is an x-intercept sitting fat, dumb, and happy right on a horizontal asymptote. It will never do that with a vertical asymptote. And that's okay. Because the horizontal asymptote only behaves like an asymptote for large values of x and small values of x. All right? So for relatively, did I say small? Very, very small. I meant very negative values of x. For these values of x kind of in the middle, the graph can cross and touch a horizontal asymptote, never a vertical asymptote. So here's what we're going to do. You remember I told you the two places that the graph can change signs? X-intercepts, vertical asymptotes, right? Right here. Those are the only two places it can change signs. And here, -4 or plus or minus 2. Those are the only places. In between those points and beyond those points, the graph is the same sign. In between any two of those points, right? And then beyond to negative infinity and positive infinity. So what are we going to do? We are going to plug in one value in every interval. Here's how this works. See this little chart at the bottom? Here's how this is going to work. Question. Your first column, x-intercept or vertical asymptote. Which ones do we have? We have, leave some space here, right? We have -4, -2, and +2. Leave space in between them. Leave some space on top, like that, right? Those are the only places the graph could change signs. It may not. It's like those are the exits on the interstate. Those are the only places you could get off the interstate, but you may not. Okay? So what we're going to do, we're going to pick one point. We're going to pick a value of x in between or in each of these intervals. 3 points divides the x-axis into 4 intervals. 3 points divides the x-axis into 4 intervals. Touche. Right? There's 4 intervals from -4 to -infinity, between -4 and 2, between -2 and 2. I'm sorry, between -4 and -2, between -2 and 2, and from 2 to infinity. We're going to pick one point in each interval. What are our points going to be? From -4 to -infinity, I'm going to pick -5. I'm lazy, so I pick even numbers whenever I can. You can't always. I'm going to pick even numbers whenever I can. And I'm going to pick low numbers whenever I can. Because I'm lazy. Between -4 and -2, being the creative genius that I am, let's try -3. Between -2 and +2, whenever 0 is an interval, pick it. Because it's easy to plug in. And we're lazy. So that's 0. Which, by the way, we already plugged in, right? When we did the y-intercept, we already know the value there. The value there is -1. Right? And then we're going to pick one point beyond 2. So I'm going to pick 3. Okay? I am going to test the function at each of those red points. Test the function at each of those red points. All right. So I'm gonna do f of 5, f of -5. So I'm gonna have -5. The numerator is -5. And let's try it. -5 plus 4 on top, divided by -5 squared minus 4 on the bottom. That's going to give me a -1 on top. And it's going to give me 25. 25 minus 4 is 21 on the bottom. The student will observe that is negative. And so you go up on your graph and you plot that point at -5. Right here, -5. My graph is barely negative, right? It's only -1/20th, right? Then I'm going to plug in -3. Let's see if it changes signs. -3 plus 4. Then I have -3 squared minus 4. The numerator, -3 plus 4 is a 1. Down in the denominator, I have 9 minus 4. That is 5. What happened there? 9 minus 4, that is a 5. That is small, but positive. So the graph did change signs at -4. So I go up to my graph, I plot 1/5. At 3, I plot 1/5. So we're plotting points, but we're doing it strategically, not willy-nilly everywhere, right? And when we go to use these points, we're going to respect the asymptotes and intercepts that we have. So now let's go the next interval. We plug in 0, we have -1. That is already on our graph right here. Then we're going to jump the asymptote, that vertical one at 2, and we're going to plug in 3. So I'm going to have 3 plus 4 divided by 3 squared minus 4. That's going to be a 7 up top divided by 3. That's going to be 3 is squared is 9 minus 4, or 5 on the bottom, which is positive. By the way, this one in the middle here is negative, right? So basically, everywhere it could change signs, in this case, everywhere it could change signs, it did. So now I'm going to put 7/5 up here at 3. So I go to 3 right here. 7/5 a little bigger than 1. It's like right there. All right. Any questions? We didn't plug in just arbitrary points. We plugged in points between places that it could change signs, between x-intercepts and beyond x-intercepts, and between vertical asymptotes and beyond. So between and beyond those places. Now we had 3 places like that here. That's this on the outside. On the left here, -4, -2, 2. Those are the 3 places that could change signs. We plugged in a point on either side of each one, determined the sign. Remember I told you? You got to see the sign. Determine the sign, we put it on our graph. So here we have those points. Now guess what we can do? We can graph it. We're going to play connect the dots, sort of, because we know the rules, okay? So I'm going to get, let's see, what color do I want here? How about I don't know, just blue, right? Well, blue will go through that. Let me do red. Oh, it's not a good color. Let's get back to blue. All right. So what's going to happen? Out here, it's going to be very close to the x-axis. So the graph is coming in very close to the x-axis here. It's going to go through that point. It's going to cross the x-axis there. And then when it gets here, what does it do? When it gets there, what does it do? It's got a fence in front of it. It's got an electrified fence. And it's not as stupid as little boys are, right? Including this little boy. It's not going to touch the fence. It can only do two things. When it hits the fence, it can go up or down. Now, I'll give you a clue. It's not going to go down. Why won't it go down? Because if it did, you would have another x-intercept right there. And you don't have one. You've already taken care of all the x-intercepts, right? So you know there's not an x-intercept right there. So it doesn't go down. It's got to stay positive. So if it stays positive, it's got to go to plus infinity. It's got to go up like this. Has no choice. Right? Now, on your graph, when you draw one in class, you are going to put dashed lines for all the asymptotes. Dashed lines. That's communicating to me that you know there's an asymptote there. Now, when it hops this asymptote, it's either going to come down from the top or go up from the bottom. It's only got two choices. Which one's it going to do? Well, it's negative right here, right? So it's got to come up from the bottom. So let me erase those. So it's going to come up from the bottom, make some kind of turn, go through our y-intercept, and then it's got to go back down. Right? It can't do this. It can't cross that and go like that. Can't do that because you'd have another x-intercept and you ain't got none. Right? Goes back down on the bottom. Now, just in case you're wondering, you see this hump right here? I'm not going to hold you to account where you put that hump. On the left side, right side, or even right at that point. You need some calculus or a calculator to determine where that hump goes. But it cannot cross and go positive. Because if it crosses and goes positive, you have x-intercepts, right? So I'm not going to, if you put the hump on the other side, if somebody else drew it like this, if you drew it like this and went back down, that would be okay. All right? Because we don't have the calculus to figure out where that hump goes. All right? Questions on that? Then what happens? It's going to jump the vertical asymptote at 2. Is it going to come up from the bottom or down from the top? Is it positive or negative on the right side of that asymptote? You plugged in a point, it's positive right here. Right? So it's going to go like this. Come down from up here. And it's got to stay positive the whole time. We're going to have other cases where it does this. We're going to have other cases where it does something like this. Right? It crosses again, comes down from plus infinity, but has another x-intercept, and it levels out negative. Right? Like that. But in this case, that doesn't happen because you don't have another x-intercept. You see? So you see that this evidence that you collect, it starts to triangulate with itself. It starts to triangulate with itself, meaning it starts to validate itself. So for example, if somehow here in the middle, you thought that the asymptote came down from up here, you knew you'd be in trouble because you have to get through this y-intercept right there, and you got a problem, okay? All right, because you'd have another x-intercept. Any questions on that? We're going to be doing 2 more of these. Have I mentioned that these are guaranteed points on the exam? Just guaranteed. I mean, you're just going to, guaranteed. Learn how to do these. Get your arrow, shoot them points, and put them in your bag. Right? Now, I'm going to show you something else. You remember we talked about multiplicities? in the last week. That's the power to which a factor is raised. Remember, if a factor, if it's raised to a power, that's a multiplicity. Now I'm going to show you something. This function, you see this function here? That's our function. Let's take a look at this y-intercept right here. I'm sorry, this asymptote. Where did that asymptote come from? Where did that asymptote come from? That's at x equal -2. It came from a factor in the bottom. You remember this bottom factored into x plus 2, x minus 2? It came from this factor right here. So this factor produced that vertical asymptote because -2 makes a 0 in the bottom. Right? Now watch. Ready? What power is that factor raised to? The first. When we were doing polynomial functions, like Monday, if a factor was raised to an odd power, did it cross the x-axis or not? It crossed. It crossed. Now, so I want you to think of crossing the x-axis as changing sign. Crossing the x-axis is changing sign. Here's the punchline. You ready? Since x plus 2, the factor from which this vertical asymptote comes, x plus 2 is to an odd power, it's going to change signs at that asymptote. It's going to change signs. That's another way to validate your plotting points. Also, at this, that one produces an asymptote too, right? It produced this one on the right at +2. Since it's to the first power, it's going to change signs there. Now, it doesn't tell you which direction it's going to change signs. It doesn't tell you positive to negative or negative to positive. It only tells you that it will change signs. And if this were x squared there, it would not change signs. It would go to infinity in the same direction on both sides or to negative infinity on both sides, if that were a 2 there. And the last thing, think of this numerator as a factor. It's to the first power. That numerator determined that y-intercept, right? Or excuse me, x-intercept. That numerator is to a first power. And by the way, this would be true with any odd power. If that were to the third power, any odd power, it's going to change signs there. If it were to an even power, if it were like squared, you know what would happen? The graph would come down here, bounce off of that, and then level out like that. If it were squared, it would not change signs. It would touch the x-axis still, but it would not change signs. So remember that rule of multiplicities. If a place that it changes signs comes from a factor to an odd power, it will change signs there. If a point or a vertical asymptote at which it could change signs, if that comes from a factor to an odd power, it will change signs there. If it's to an even power, it will not. We're out of time. Stay warm, well fed. Come by and see me if you need help. I really, really want to help people do good at this.